Good afternoon to everyone in India and good morning to everyone in Europe. And welcome to this webinar entitled Membrane Technology in Water Treatment and Water Reuse. My name is Joel Fernandez and I'm the Regional Director for the European Business and Technology Center based in Mumbai. Today I have the privilege to welcome Chris Dotremont, who is a project manager for VITO. VITO is a leading European research and technology organization in the areas of clean tech and sustainable development, elaborating solutions for the large societal challenges of today. VITO provides innovative and high-quality solutions whereby large and small companies can gain a competitive edge and advises industry and governments on determining their policy for the future. Welcome, Chris, to this webinar, and I welcome all of you who have joined us today. Before we start the webinar, I would like to lay down the housekeeping rules and how to function with the tools that we have been given you. As of now, all the participants are on mute. If in case you would like to unmute yourself to ask a question, you would need to first raise your hand, whereby you can see a little icon on your toolbar showing you where to raise your hand. As soon as you raise your hand, I get intimated that you are looking at asking a question, and then we will unmute you and you can ask your question. I'm sure most of you are familiar or already familiar with the EBTC webinar and how it works. So let me start off with a little presentation on EBTC. The European Business and Technology Center is is the only center in India focusing on clean technology transfer from Europe to India. We have a pan-India presence in New Delhi, Mumbai, Bengaluru, and Calcutta. That's where we have our offices. We work with 39 partners, and VITO happens to be one of our partners and is also going to be making this presentation today. So I'm very happy to have a partner organization of EBTC present today. EBTC focuses on 4 sectors: biotechnology, energy, environment, and transport. And we are the only center dedicated to promoting European clean tech in India. And we've been very successful ever since we've started in 2008. And we are happy to have organized or co-hosted this webinar with VITO. So without any further delay, I would like to put it, pass this on to Chris, who will take us through her presentation. Chris, over to you.
Good afternoon in India and good morning in Europe. So my presentation will focus on membranes in water and wastewater. What is a membrane to start with? Well, it's a semi-selective barrier between 2 phases, and in our case it's always a liquid phase. And you have a driving force over the membrane that can be a pressure, but it can be for other types of membranes. It can be a concentration difference or an electrical potential difference. In case of water applications, most of the time we are referring to pressure difference. The efficiency of the membrane process is determined by permeability or flux, and flux is the amount of liquid, in our case it's water, that is transported through the membrane per time unit and per area unit, per square meter. And of course another parameter of efficiency is the selectivity and the retention of the process. These are the different types of membranes that are important in membrane processes in water applications, going from large pore size, microfiltration, to lower pore size, ultrafiltration and nanofiltration, and then finally it's a non-porous, so to speak, membrane, reverse osmosis. And depending on the pore size, because the mechanism, the the separation mechanism is a sieving mechanism. So the larger the pore size, the larger the components that are retained. So for microfiltration, these are suspended solids. For ultrafiltration, macromolecules. For nanofiltration, small organics and multivalent ions. And then finally, reverse osmosis, it retains everything that is still in the water, so the ions, the salts. And sorry, this gives an idea with microfiltration. So you remove all the solids and part of the bacteria. With ultrafiltration, you have a better removal of microorganisms, which is also important if you want to reuse the water in, for instance, drinking water applications. And nano and filtration and reverse osmosis are used for desalination mainly. The membrane market, it's a growing market, 10 to 20% annual growth rate. And with the pressure-driven processes that are applied in the water applications, and I'm referring to microfiltration, ultrafiltration, reverse osmosis, and nanofiltration, you have more than 75% of all the membrane applications. So it's the big market, so to speak. The classification of membranes, well, you can choose different parameters to classify them. Pore size is the usual way to classify them. I mentioned it before already. But you can also classify them according to the structure of the membrane. The membranes that we are using in water application, they can be homogeneous in one material, so to speak, or they can be heterogeneous. And most of them are porous, and yeah, reverse osmosis is non-porous. The material, most of the membranes used in water applications are polymeric materials, but you have inorganic membranes, ceramics for instance, that are also used in water applications, but it's a minority. And then you have different configuration and all of them are used in water applications. I come back to that later. You see that the majority of the membranes that are used worldwide also, but certainly in West European market, are polymeric membranes. It's only a minority that consists of inorganic materials, and most of the time they are used in wastewater severe conditions with acids, and so extreme pH and etc. So for the classical water application, normally you use polymeric membranes. And the pressure-driven membranes, they have normally a very thin skin layer, so they are asymmetric. The skin layer gives you the good selectivity, and underneath you have either a finger-like structure or a sponge-like structure. Both exist in the water world, but this structure is necessary to give you the mechanical strength. And it's only in the skin that you have the selectivity. This is, of course, to have high fluxes and have good selectivity. The type of materials that are used, most of the time you have either hydrophobic polymers, PVDF and polypropylene and Teflon, but for classical pressure-driven processes, it's most of the time PVDF or polyether sulfone, and for reverse osmosis, it's a thin film composite structure with polyamide on top of a classical polysulfone ultrafiltration layer. So this is it's an asymmetric structure, and it's a non-homogeneous. You have two layers on top of each other. The module configuration then, you have flat sheet available. You have, but in water applications, normally the flat sheet is wrapped around a tube for the permeate collection, and this is the way you make spiral wound membranes. And I would say 90% of the membranes in water applications are in spiral wound. If they are flat sheet, they are in spiral wound. The flat sheet can also be used as a flat sheet in a stack, and that is then for membrane bioreactors. The spiral wound are mainly used in reverse osmosis and nanofiltration. Tubular membranes, you subdivide them depending on the diameter of the tube. You refer to tubular if the diameter is above 5 millimeter. These can be used in MBR, membrane bioreactor applications. Capillaries have a diameter between 0.5 and 5 millimeter, and hollow fibers, they are very thin. They have a diameter below 0.5 millimeter. And at the edges, you need to pot them in an insert. And this is the housing of the hollow fibers. So at the end, you need a sealing, and this is done by, most of the time, it's a resin that is used for potting. And then you have the possibility to flow from the inside of the capillary to the outside. That's what's called inside-out filtration. Or you can also flow from the shell side to the inside of the capillary for the extraction of the permeate, and that is called outside-in. All these configurations are in use for water applications. The features of the different configurations, well, you have to decide which type of configuration you use depending on a number of parameters. If you have very dirty water, then cleanability is very important. Then you choose, for instance, a tubular or a plate and frame. If you have an easy water, surface water, with low fouling capacity, then you choose for instance, for a hollow fiber with a very high packing density and low investment cost. So it depends a little bit on the applications. Another way to see at the packing density is area per volume, area square meter per volume of the module, and then you see that the champion in this for this parameter is the hollow fiber configuration. So if footprint is important and the water quality is okay, then you normally choose for hollow fiber, if they are available, of course. And here is the availability. Micro and ultrafiltration, they are available under tubular form and capillaries and hollow fibers. Nanofiltration and reverse osmosis, they are most of the time in spiral wound configuration. So then you don't have the choice, of course. Mode of operation, you can operate in a dead end. That means that the feed is flows perpendicular to the membrane surface, like a coffee filter. Another way is you flow the feed across the membrane, and part of it is then converted into permeate, whereas in dead-end filtration 100% is converted in permeate. A semi-dead-end operation is you combine a dead-end operation mode with a backwash. So from time to time you revert the flow and you backwash with clean water the filter, and of course you have to discharge then the cake layer. Then you can choose for a single pass-through or one pass-through. That means that the feed is passing one time through one membrane module, or you can recycle part of the flow. This is a typical configuration for membrane bioreactors. In that case, you submerge the module in the tank. We call it the membrane tank. It's filled with sludge in that case, and you suck out the permeate. So it's an outside infiltration, and this is typical for membrane bioreactors. And this is a classical configuration. It's a Christmas tree configuration, typical for reverse osmosis. You have multi-stage configuration, and the permeate is collected at each stage, and the concentrate is sent to the next stage. Of course, part of the feed is already converted into permeate, so the second stage needs less surface, so you reduce the number of tubes. These are the high pressure tubes where the membranes are inserted. And if you have a multi-stage system, you can go to higher recoveries. That's the reason why you stack them in multi-stage configuration. Okay, let's go now a little bit deeper into micro and ultrafiltration. So we've seen the last 10 to 15 years really a boost in micro and ultrafiltration as a replacer of classical sand filtration, for instance. Why? Because they are micro and ultrafiltration, they form an absolute physical barrier. That means that bacteria, viruses, algae, they are nearly 100%. Here you see the log removal, so they are very well retained by certainly ultrafiltration. So this is important. You will create very good quality of water for irrigation purposes or to post-treat, for instance, with reverse osmosis. And one of the reasons that UF and MF are so successful is that there was a development in hydrophilic membranes. Remember the PVDF, which is in fact a more hydrophobic polymer, but there are ways to make it more hydrophilic so that you have higher fluxes. You can do it also, you can do it by surface modification, or you have a blend of polymers, for instance. The result is a low pressure membrane, high permeability membrane, and then you have less fouling because you have less compaction of the cake layer. So we see a lot of improvement, and for surface water treatment, for instance, a classical yield is a flux of 100, which is quite high, and a membrane lifetime above 5 years. And then this is for all membranes. They are modular and they have a small footprint. So these are other advantages. The materials, well, we mentioned already. So mainly it's polyether sulfone, and this is a copolymer, PVP, polyvinyl pyrrolidone, and PVDF. This is polysulfone and cellulose acetate, but they are less used. So let's say the first two are mainly used. And these are the classical size of modules. And recent developments, these are the multi-bore membranes of Ingen. Ingen is taken over now by BASF, but it's a new development. Or also ceramic MF membranes for water treatment. This is the Ingen BASF membrane. So you see one capillary that contains inside 7 smaller capillaries. So it combines a high mechanical resistance with a high surface area. And here you see the ceramic microfiltration. This is a Japanese development from NGK. And yeah, they claim very high fluxes. But there is no standardization. That is one of the disadvantages in ultra and microfiltration. You see a lot of configurations, and once you have decided for one configuration, yeah, it's difficult to change them. Here you see a lot of configurations that are applied. So we call it proliferation of module types, orientations, and geometries. This is a list of suppliers. Kubota is number 1 in MBR, flat sheet. HF is hollow fiber. FS is flat sheet. Here you see number of well-known suppliers, for instance Dow, GE, so these are the really big ones. But there is a huge proliferation of different suppliers, and they all have their own configuration and module size. So what do you need to choose in case of an easy water? Easy waters are low in suspended solid content and low in organic content. Then you can choose for a small diameter and inside-out filtration. But if you have more difficult waters with high suspended solid, high organic contamination and even sludge, then you have to choose for other configurations. For instance, if you still want to choose for a small diameter, we recommend outside infiltration. We also recommend larger diameter or even submerged systems with hollow fiber modules. Then there is a reinforcement on the hollow fiber so that you can backwash. And of course you also have the flat sheet for the more difficult waters. For easy waters, you can choose for a semi-dead end operation for surface water and ground and well water, but for more difficult waters, we recommend cross-flow. And this is a typical semi-dead end operation for surface water treatment, but also we use it also for MBR applications. So you have a typical cycle in dead end, and then you revert the flow, and then you go into backwash, and you start again a new filtration cycle. This is when the operation is very stable. You start after the backwash again at the initial TMP, so you have no fouling on your membrane. You only have a cake layer built up, but no irreversible fouling. So a typical filtration cycle in semi-dead end is 20 to 60 minutes. And these are the typical fluxes. The backwash is typical 20 to 60 seconds, and the flux of the backwash is normally higher. And this is to have some force on the membrane to remove the cake. Of course, you need from time to time a chemical cleaning. You can do an enhanced maintenance cleaning. This is once a week, for instance. Or you can really go for a severe cleaning with soaking time and sodium hypochlorite at higher concentrations. This depends on the degree of fouling. So again, this is the slide I showed before. So you have stable operation, but sometimes it can go wrong. And this is when it goes wrong. When you see this appearing, then you are in trouble. That means that you have not a stable operation, and you see that the initial TMP after backwashing is rising, meaning that you have irreversible fouling. And then you have to decide on a number of critical parameters like flux. You can decrease flux or you can decrease the recovery. It depends sometimes also on the feed quality, and then you have no choice, but you can anyway decrease flux and recovery. And of course, it depends also on the module type. But here you see a couple of figures. This is the TMP in time for a 100 LMH flux, and here you see that it becomes very unstable at 200 LMH. Or you can play around with the filtration cycle time. If you choose for 15 minutes, you can operate stable at 100, but you still can operate it stable at 200 LMH at a shorter filtration time. You can combine the backwash with a forward flush to eliminate the dirt from the feed side, or with an airlift. Also outside in can use air, but then you need an hydrophobic membranes. It's not very much in use. For outside in, and this is more typical for MBR applications, then you have relaxation in case you cannot backwash. This is, for instance, the module of Pentair, former Norrit company. They have tubular membranes and for MBR applications, and they combine it with an airlift. They call it airlift, but it's also an air scrubbing. You can dose flocculant in line also to make the operation more stable. Without flocculant, then you have a very compact cake. In case you add flocculant, you have a more porous cake, and that also allows you to keep the system more stable. Here you see without flocculant and with flocculant, TMP over time. So the flocculant allows you to delay the cleaning, and in case the dosage fails, you see immediately that there is a problem. So you need to make sure that your dosage is working. Okay, these are the advantages I already mentioned on dosing flocculant. And these are the number of applications that you can have in water, MF and UF in drink and process water treatment, pre-treatment in the preparation of ultra-pure water, recovery of rinsing water, purification of chemicals, and you can imagine a number of other applications. There is one case, but I will not go into detail because of time limit, but you will have the slides later on, and you can see how the conditions are, the objectives, the water treatment scheme, here schematically. So it's the implementation of a double barrier system, UF and RO, in combination with ion exchangers, that was applied in the Netherlands. It was one of the first full-scale installations. Here you see the amount of surface they chose for inside-out filtration based on the Pentair modules, and they obtained a recovery of 95%. But in the beginning they had problems. This is the reverse osmosis. It's a two-stage system with DAO membranes inside and a water recovery of 90%. So these were the problems. At the beginning it was under-dimensioned, so they had to install 2 additional UF streets, and meanwhile they also add inline dosage, and since then they are very satisfied with the installation. I skip this one. This brings us to reverse osmosis and nanofiltration. Reverse osmosis is in fact at this moment in most of the world number one technology for desalination, except for the Middle East, but that is because of historical older installations based on thermal processes. So you see that from, let's say, end of 2000, reverse osmosis is a dominant technology in seawater desalination. And this is mainly because of the energy recovery on the brine side and the improvement on the membrane and the modules. So you see at this moment, RO plants are typically 5 to 10 times more energy efficient compared to classical thermal desalination plants. This gives you an idea how well the improvement was. From 80 up till now, we have a cost reduction factor 7, we have a flux that has been doubled, and also a factor 7 better retention in salt. So there has been a lot of improvement. Also with the turbine on the brine side, you can recover a lot of energy. So a typical large-scale plant has an energy usage of, let's say, 3.5 kilowatt-hour per cube. This is for large-scale plants. So you see that the upper band is for smaller installations, and the under band is for the large-scale installations. And these are costs for desalination, so they are very low. The difference with nanofiltration, well, this is a reverse osmosis membrane, so the salt retention is high, above 99%. And in fact, the nanofiltration is, so to speak, a reverse osmosis membrane with defects. And the larger the defects, it's a controlled way of having defects, but the larger the defects, the lower the retention. And you see for nanofiltration that you have for monovalent ions a low retention and for multivalent ions a high retention. So for nanofiltration, it's one of the youngest pressure-driven process, and it's also growing, especially in drink water applications. So for partial desalination, softening of drinking water. In case of NF and RO, they have a spiral wound configuration. This means that the water should be pre-treated carefully. So you have to remove suspended solid, you have to remove dissolved components like ions that can scale, or you have to do something to avoid scaling, because you will retain ions. And biofouling, also to avoid biofouling, you need pre-treatment. So you have to avoid fouling, and that means an extended pre-treatment. And here are you can pre-treat the water with, preferably by ultrafiltration to have the best quality. In addition, you can dose biocides, or you can do a pH conditioning to avoid scaling. In case you have chlorine in the water, you need to remove it for the polyamide membranes, otherwise you have damage of the membrane. And then you need also to dose antiscalants. These are a number of suppliers. The number one is Dow, and the number two is Torre. But these are well-known suppliers of NF-RO membranes. And this is an example. I was involved because I was working for Keppel Segers at that time in this plant. It's in Ulu Pandan in Singapore, and it's for the production of new water. And it's a public-private partnership with PUB, and it's one of the biggest in the world, 6,000 cube an hour. So the effluent coming from the biological activated sludge system is pre-treated carefully with a strainer, then with in this case, a UF membrane, and then a reverse osmosis, and then the new water storage tank, and then it's ready for distribution. This is how it looks. It's a real water factory, so to say, and these are the typical energy figures for the whole plant. This is the reverse osmosis part. Okay, this one I will skip due to time concerns. MBR, in that case, you have an activated sludge reactor. This is a classical reactor where you have a bioreactor and you have a settler. Okay, in case of you have a sedimentation problem, you have a bulking of the sludge, then the effluent quality goes down. Also, you have a large footprint, so why not submerge a membrane in the bioreactor tank? The effluent quality is much better. You can keep the sludge in the tank anyway, also in conditions where there is bulking, and the quality is better, so you can reuse the water. And then there are two systems. You have an external loop. For instance, the Pentair tubes are used in an external loop in cross flow, or you can submerge the system. Most of the systems that you find in MBR world are submerged. Submerged, well, you need more surface, but you have a lower working cost. In case of an external loop, you have the cross flow, so this is higher working cost, but you need less surface, so lower investment cost. Here are the typical fluxes for a submerged system compared to an external system, and the typical energy consumptions also. In case of a submerged system, you need air scrubbing to clean the membrane. So this is, of course, also an additional cost in energy. In case of MBR, you can have higher sludge concentrations from 10 to 15 up to 30 gram. Of course, this is a little bit higher. Normally, for typical MBR, it's about 15 gram per liter. You have higher sludge viscosity, means lower oxygen transfer. You have to take that into account, but the big advantage is smaller footprint and also a lower sludge production. You have a higher sludge retention time, and so you can decouple the sludge retention time with the hydraulic retention time. Typical hydraulic retention time is it's minimum 4 hours, but typically is 8 hours. Also, the flux will be a little bit smaller compared to a classical activated sludge system. Here you see how a module looks like if you lift it out, and you see that there is a lot of clogging. So a pre-treatment is again very important to avoid this clogging. And this can be done with a fine grit, but yeah, 3 millimeter is in fact necessary for flat sheet membranes. But for the hollow fibers, you need a coarse filter of 1 millimeter minimum. And here you see what can happen and the interactions between the biomass and the membrane that can cause fouling and clogging. But also the membrane module characteristics play a role. You need the proper aeration, and of course the way of operation is also important to control everything. So normally you have in MBRs a relaxation period for the flat sheet because you cannot backwash. For the ones that can be backwashed, the reinforced ones, then you have a filtration and a backwash. In case of the flat sheet, normally you have a filtration and a relaxation. This is the way of operation. And then you need also enhanced maintenance cleaning, and sometimes you need also a severe cleaning, 1 or 2 times a year. So here you see the physical cleaning with air or with relaxation. A chemical enhanced backwash is with some addition of chemicals at low concentration, but you can have a severe cleaning at high concentration, and yeah, that's in case that they are severely fouled. Again, the configurations going from flat sheet, tubular to hollow fibers, you have them all. Here are a couple of suppliers. Kubota is the #1 in flat sheet. Huber, it's a European player, a German one. They have also flat sheet, and it's a rotating system. Xenon is in fact the #1 for MBRs. Xenon is acquired by GE, of course. They make use of reinforced hollow fibers. This is a Koch-Puron type of module, so they are potted at the bottom side, and the top side is open. This is the X-Flow, but now acquired by Pentair. So these are the tubular ones with airlift. Okay, one of the main advantages of MBR is a smaller footprint, but also the better effluent quality, so that you can send the water directly to a reverse osmosis unit for reuse. And these are typical energy consumptions for the aeration in the MBR, and this is for the sludge recycling. So you see that the external MBRs, they use more energy compared to the submerged systems with air scrubbing. Also in MBR you see a lot of evolution the last couple of years, so the costs went extremely down in the end of the 90s, and now it levels off to about $50 per square meter in module. This is more divided into yeah, categories like capital cost and operating cost. So I suggest you have a closer look at it later. But you see that the costs went down dramatically. And then this one I will also briefly touch upon. So these are two, it's a comparison between two MBRs with the same type of membranes, but North Canal in Germany is a larger plant, and Varsseveld is smaller and has a separate MBR tank, whereas in North Canal you have it integrated, so the membranes are submerged in the aeration tank without any division into a membrane tank. And again, have a closer look at it later, but these figures are quite similar, except that Karst North Canal is larger, and this results in a lower cost for Karst for two reasons. It's a larger system, so the economies of scale, but also because it's an integrated system, whereas for a separated system you pay a little bit more, and this is also a smaller system. And these are the operational costs, again, for the Karst North Canal against Varsseveld. You see that, well, if you take everything into account, also the cost for sludge disposal takes one third of the total cost. The chemical consumption is important, and of course energy. This is the energy part. And then I have a couple of minutes left to give you, I briefly touch upon a couple of developments. There will be later on a workshop. It will be the last week of November, and then we will elaborate more in detail, especially on the MBR part, because that is an application that's close to the market, where we are going into a spin-off in the course of next year. And that's the first application, whereby we have a textile that we coat on both sides simultaneously, and this gives you an envelope for outside infiltration. And the advantage is that the membrane is well anchored on the textile. It's like a reinforced envelope, like in case of hollow fiber you have also reinforcement. So the big advantage is that you can pack wash this membrane up to pressures of 2 bar. So we call this a real backwashable flat sheet membrane. And we are in collaboration with a company that makes modules out of it, and we are at this moment testing these type of membranes for wastewater treatment, domestic one, and we can have fluxes up to 55 LMH under stable conditions because of the backwash. Here, these are the advantages summarized. So an improved fouling control, fluxes up to 50% higher. We have a higher packing density compared to Kubota because the thickness is only 3 mm, whereas a Kubota envelope is 6 mm. It's a robust design. With a triple deck configuration, we have low aeration, and we can produce it at a competitive cost. Another development is hydrophobic membranes, and we see the application in membrane contactors, more specific for membrane distillation. So it's a technology that I didn't touch upon during the presentation, but it's another way of desalination, making use of thermal heat. And we are looking at different ways of coating the membrane. So we focus on a hydrophilic cheap membrane that we coat in one of these ways. And the final goal is to have a membrane that performs better. These are fluxes for the base membrane, but coated, for instance, with a dual layer gives us already fluxes above 20, higher than the classical Teflon membranes under moderate conditions, because you can have higher fluxes if you have a delta T of 50 degrees. We only have a delta T of 15 degrees. And then the last last development I want to show is on ceramic membranes. We normally develop them for solvent filtration, but we have one development on water applications whereby we modify the ceramics. So it's a Grignard reaction, a patented method, and the OH is replaced by a R. In case of water applications, this R is an hydrogen, and this gives very good results. For instance, this is a membrane, a native one, and these are different solutions filtered over the membrane. You see fouling, but if we have the membrane modified, you see that the membrane is not irreversibly fouled. And you can use it for all kinds of waters, and it shows a very stable operation. Okay, so these are quickly a number of developments at VITO, and I also want to highlight that we have a last seminar on Monday, next week Monday, and this will be on membranes in biorefineries. So this is my presentation, and I recommend also the next seminar next week. Are there some questions?
Thanks, Chris. Thanks, Chris. Thanks for that very interesting presentation. This is Joel Fernandez from EBTC. I will be moderating the questions. If in case any one of you have a question, please raise your hand by clicking on the toolbar where you see a hand, and I will unmute you and you can ask your question now. Or you can also post your question if you have one.
Or they can send me an email later on.
Yes, Chris, would you like to share your email address with everyone?
Yes.
Chris's email address is chris.dotremont, D-O-T-R-E-M-O-N-T, at VITO.be, B for Bombay, E for England. You will all be receiving a copy of this webinar with the links as well as the slides. So if in case you have any further questions, you can always address them directly to Chris. I'm going to put Ashish Sahu on the spot. Ashish, may I request you to ask a question that, because the last webinar that we did on Monday, you were very interested and you asked a question then. I'm sorry to put you on the spot, but I think you came up with some very good questions the last time. Ashish, I'm unmuting you right now. Ashish, we can hear you. I guess not. So in that case, we can wrap up this webinar 10 minutes before time, which is fine. And we can, we will be sending you the information, the slides and all of that after this, but also with your feedback, so you can share your feedback with us. And don't forget to register for the next webinar, which will be on biorefineries, membrane applications in biorefineries, which is scheduled for the 12th of October at 2:30 p.m. India time and 11 a.m. Europe time. So thank you everyone for joining us today, and feel free to send Chris your questions directly. Thank you. Thank you, Chris, and thanks everyone at VITO.
Thank you for organizing the webinar. And thank you all the audience.